Welcome to the Deep Dive. You are plugged into the information ecosystem that matters, and today we are going deep on an architectural breakthrough that is, well, it's already shaking the foundations of AI research.
It really is.
We're talking about a moment that the industry is starting to call the 2017 transformer moment for AI reasoning.
And that's not an exaggeration.
A relatively small, six-person startup named Poetiq AI has seemingly changed the game for artificial general intelligence AGI reasoning in a single stroke.
Okay.
And they did it not by building a bigger model, but by designing a smarter system.
It's a genuinely stunning development. I mean, it tackles head-on this central paradox that has frustrated researchers for, the last 2 years?
Right.
We spent billions developing these massive, powerful foundational models. Think of the scale of a Gemini 3 Pro. These things are capable of handling 1 million tokens of context, trillions of parameters.
This is huge.
Huge. Yet, when you put them in front of a problem that requires genuine fluid intelligence, something that requires adaptability, abstract rule inference, they just hit a wall. They could retrieve facts perfectly, but they couldn't reason their way out of a novel challenge.
So all that power was just stuck.
Exactly. And the sources we have today, they detail this breakthrough meta system, this architectural wrapper, or as Poetiq calls it, scaffolding, that just completely solved this exact problem. It essentially unlocks the reasoning potential that was already sitting there, latent inside these massive, expensive models.
Okay, so let's unpack this entire picture for you. Our mission today is to break down this monumental achievement by Poetiq AI on the notoriously difficult ARC-AGI-2 benchmark. We have some amazing source material, everything from their white paper in the GitHub repository to internal ARC prize analysis that reveals the precise mechanics of this scaffolding, the dizzying numbers that prove its efficiency and why this specific type of architectural shift is being compared to that foundational leap the transformer model gave us back in 2017.
And it's so important to stress this. This isn't just about, tweaking some hyperparameters or training for a bit longer. This is a paradigm shift in how we orchestrate intelligence. It is about the architecture of the reasoning process itself.
We have to start with the headline data points because they are truly shocking. On November 20, 2025, Poetiq announced they had absolutely shattered the state-of-the-art on the ARC-AGI-2 benchmark.
Shattered is the right word.
The leap here is what stunned researchers globally. If you look at the raw capabilities of the underlying model, Gemini 3 Pro's baseline performance was, 31.1% accuracy?
Yeah, about that.
Poetiq layered their lightweight system on top of that raw model and pushed the performance to an unprecedented 54%.
And that jump, that's only half the story. That 54% gain comes with this profound, almost unbelievable efficiency. I mean, look at the cost angle. Poetiq achieved this result at a cost of just $30 per task.
$30.
Now, you have to contrast that with their closest, albeit very distant, competitor, the Gemini 3 DeepThink configuration. DeepThink only managed 45.14% accuracy, so almost 9 full points lower, but it cost $77.16 per task.
Wow.
Poetiq delivered dramatically superior performance at a nearly 2 times efficiency gain. It just proves that computational complexity is not a proxy for intelligence when you have the right architecture.
That jumped from 31.1% to 54%. That's a massive, sudden plus 22.9% improvement. What was the initial reaction? I mean, did the research community even believe this at first? Was there, skepticism?
Oh, absolutely. There was very healthy skepticism, which, to be fair, quickly turned into admiration once the verification process was complete. The sheer speed of the adaptation was just striking. This breakthrough was achieved in a matter of days after the core foundation models were even released.
Days.
What's fascinating here is that the 54% performance is now edging right toward the 60% human baseline, based on those crowdsourced cognitive panels. This signifies a pivotal shift away from just scaling model size, the massive parameter count, and towards system design.
So it's about being smarter, not bigger.
Precisely. The innovation is that the scaffolding is lightweight, and crucially, it's model agnostic. Poetiq demonstrated this portability right away. They integrated both Gemini 3 and, get this, OpenAI's GPT 5.1 within hours of their respective releases. It just confirmed that the architecture itself is the key, not the specific vendor model you plug into it.
Okay, to truly grasp the significance of that 54% score, we really need to understand the proving ground itself. ARC-AGI-2. Why is this benchmark so different and, frankly, so much harder than what the public usually hears about? Things like MMLU or coding benchmarks where models are already exceeding 90%.
That's the critical context that's missing in most of the headline summaries. Benchmarks like MMLU, they primarily test knowledge retrieval, deep context understanding, pattern matching. A lot of it can favor memorization or just really good recall from the training data.
Right.
ARC, which stands for Abstraction and Reasoning Corpus for Artificial General Intelligence, tests something entirely different: core fluid intelligence. It was designed by Francois Chalet back in 2019 precisely to resist memorization and retrieval.
So it's basically a pure IQ test for an AI.
Exactly. It checks rule inference, compositional reasoning, adaptability, all the skills we associate with genuine human-like creativity. The tasks are purely visual puzzles. They involve transforming these colored grids, which can be tiny, like 1 by 1, or huge, 30 by 30, using 10 distinct colors. You get a few examples, maybe 2 to 5 input-output demonstrations, and you have to infer the abstract rule, the underlying function, and then apply it correctly to a brand new test input.
And here's the element that makes it so challenging, right? The crucial constraint is that no task ever repeats. The solutions genuinely require abstract creative thought to kind of reverse engineer the hidden function. It could be complex mirroring, rotation, scaling, or even a multi-step composition of several rules. If a model can just memorize a solution, the benchmark is invalidated.
And that is why the scores, even for the most advanced models, have historically been so low compared to those knowledge-based tests. It's a true test of reasoning from first principles.
Let's track the history here a little bit. This is actually the second version of the challenge.
Mm-hmm.
Can you explain the benchmark evolution and why, even with these phenomenal foundation models, the score seems stuck for so long?
Right. So the original ARC-AGI-1 saw really rapid saturation. By mid-2025, the frontier models were hitting 75%, even up to 87.5%. Gemini 3 Pro, for instance, performed really strongly on V1 at a very low price, something like 79 cents per task.
Okay, so you basically solved.
More or less. So the ARC prize organizers, they needed to increase the difficulty exponentially. ARC-AGI-2, which they unveiled in 2025, accomplished this by introducing significantly larger grids, much more difficult multi-step compositions, and this is crucial for our discussion's stricter efficiency constraints. They instituted a $0.20 per task cap for certain prize categories, forcing solvers to be efficient, not just powerful.
So before Poetiq came along, what was the state of the art? What was the number to beat?
The SOTA was only 37.6% from Claude Opus 4.5 thinking, and that already cost $2.20 per task, which shows you how that cost-benefit ratio was scaling really poorly.
So more money for not much more performance.
Exactly. The human baseline, by the way, which they derived from panels of crowdsourced solvers, is only around 60%, and humans average about 147 seconds per task. So when Gemini 3 Pro achieved raw 31.11%, that was already a record baseline performance.
Right.
Then came the high compute attempts. DeepThink pushed that to 45.14%, but as we mentioned, at an astronomical $77.16 per task. This just confirms the logarithm problem. Massive compute for minimal gains. Poetiq's 54% on the same benchmark, verified on semi-private evaluations, suddenly reframed the entire frontier. It proved that architecture could beat brute force.
And it's important to understand this wasn't just benchmark gaming.
Not at all. Poetiq system was designed to be ARC-AGI-2 naive during its initial adaptation phase, which ensures it couldn't have benefited from any accidental data leakage.
Let's drill down now on the specific metrics cited in Poetiq's GitHub repository. Beyond the massive overall score jump, what exactly does this system deliver?
Well, the overall accuracy gain is the headline figure for sure, that massive plus 22.9% improvement over the raw Gemini 3 baseline on ARC-AGI-2. But the mastery is confirmed by their performance on the older version, ARC-AGI-1, where their advanced configurations hit 95% accuracy.
95%.
They're validating the refinement methodology on a known saturated domain, proving that their method achieves near-perfect fluid reasoning on everything except the most complex edge cases in V2.
The efficiency angle is maybe the most shocking part to people who are used to the idea that higher performance means exponentially more compute time.
The efficiency is phenomenal, and it's due to the architectural constraints they self-imposed. The system is engineered to adhere strictly to the core competition rules, which enforce a strict 2-attempt limit per task. Poetiq manages this 54% accuracy with only 1 to 2 API calls per task.
That's it.
That's it. And look at the token efficiency, which is where the rubber really meets the road. For 80% of their successful solves, they use less than 2,000 tokens in the entire reasoning loop.
Can you give us a concrete example of that token usage, something specific?
Sure, let's take task 2B387 BC. It's a task that requires recognizing rotation and filtering operations. Poetiq solved it using only 772 tokens and took 188 seconds.
188 seconds. That's incredibly close to the human average of 147 seconds.
It is. The tokens are being used surgically, not just thrown at the problem. The time component is also key. The system is thinking almost as fast as a person.
That's astounding.
Yeah.
And they've also demonstrated that this architectural method can dramatically democratize access to high-level reasoning. Can you tell us more about the cost Pareto frontier they established?
This is a huge development, especially for the open source community. Poetiq released a configuration, Poetiq GPT-OSSB, that uses an open source foundational model like GPT-OSS120B and just applies the scaffolding. That configuration manages to hit 40% accuracy on ARC-AGI-1 for less than 1 cent per task.
Less than a penny.
It moves the cost of accessing high-level abstract reasoning from the realm of megacorporations to literally anyone with a credit card balance of less than $1. It completely changes the accessibility equation for developing and running these kinds of systems.
And this isn't just about cheap computation. It's about solving the really tough, previously unsolvable problems.
Exactly. I mean, if the system only solved easy tasks cheaply, it wouldn't matter. But the solve logs confirm this is not brute force or some kind of statistical luck. The scaffolding successfully cracked known hard tasks like 65 B59 EFFC, which involves inferring and applying complex scaling operations in 3 dimensions, or DD6B8C4B, which requires inferring and applying multiple sequential rules that interact in subtle ways.
And these are tasks where the raw models just fail.
They fail natively almost every single time. This is concrete proof that the scaffolding is genuinely enabling emergent, abstract reasoning capabilities that weren't accessible through raw model capability alone.
Okay, let's move to the technical core now, because this is where the real deep dive happens. We've established the scaffolding is revolutionary, but what is it exactly? You mentioned Poetiq's refinement methodology. Can you walk us through this recursive agentic loop that orchestrates iterative reasoning?
Sure. The core philosophical innovation here is treating the large language model not as an oracle, a black box where you input a prompt and just get one final answer, but as a programmable reasoner.
The programmable reasoner.
Poetiq designed the scaffolding to engage the model in this continuous stateful loop of problem solving and self-correction, which kind of mimics human scientific inquiry. The agentic loop follows 5 specific sequential steps: plan, code, age, test, or audit, refine.
Okay, so let me see if I've got this. The initial prompt asks the LLM to create a high-level plan for solving the ARC task. Then it instructs the model to write the code, the executable function, to execute that plan on the grid. After execution, the system tests the result against the provided demonstrations. Then an independent module audits the quality of that test. And finally, it instructs the LLM to refine the original plan and code if the results fell short. That sounds like a meta-level operating system for the LLM.
It is precisely that. It adds statefulness and self-correction to models that are otherwise stateless. They just respond to the most recent prompt. And critically, as we noted before, this scaffolding is entirely model agnostic. The sources confirm that Poetiq demonstrated seamless portability by swapping between Gemini 3 and OpenAI's GPT 5.1 within hours of their public releases, with only minor API adjustments. The architecture is the product.
Okay, let's break down the individual components that make this intricate loop work, starting with the meta adapter. What is that?
The meta adapter is fascinating because it is so lightweight and decentralized. It's often run on an open source model, for instance, a fine-tuned version of Llama 3.1 405B. Its function is crucial. It is pre-trained on a vast amount of non-ARC data.
Non-ARC data, that's a critical detail.
It is. This data isn't about specific grid puzzles. It's about general programming logic, common pattern recognition frameworks, decomposition strategies, tool use methodologies. Essentially, it's teaching the meta adapter how to think about problem solving. It uses this knowledge to generate these highly specific, structured prompts and workflows that guide the primary reasoning model, like Gemini 3. It sets the context and the structure for the reasoning steps before the expensive LLM is ever called.
So the cheap local meta adapter handles all the strategy and structure, which lets the expensive Gemini 3 focus only on executing the complex reasoning steps.
Exactly. And that is what allows for that spectacular efficiency. The meta adapter itself is incredibly cheap. It costs just 0.001 cents per task to run, which ensures the strategic overhead doesn't eat into the budget.
The next component is the dynamic multi-LLM orchestration. We mentioned the cost trade-off earlier. How does this orchestration layer manage the complexity and budget dynamically?
The orchestration component is really where the cost optimization happens. It dynamically manages the trade-off between latency, cost, and the maximum achievable accuracy. We see this really clearly when we contrast their internal configurations. The simplest one, Gemini 3A, is a single-call configuration. It's designed to be cheap, about $10 per task, and it achieves 48% accuracy. This is great for, say, rapid deployment, but then you have their high-performing version, Gemini 3C. It utilizes the full refinement loop, which often involves 3 sequential calls to the model, factoring in the meta adapter and the self-audit. This naturally raises the cost to $50 per task, but it hits that industry-leading 54% accuracy mark.
So the user can decide what's more important, cost or the absolute best performance.
The orchestration layer dictates that. A user sets a budget cap, and the scaffolding auto-optimizes which configuration A, B, or C to run, offering this clear Pareto frontier between cost and performance that is dictated entirely by the scaffolding design.
So if I set my budget to, say, $40, the system automatically runs configuration B, which is maybe a 2-step refinement, and it maximizes my score for that price point. That makes sense. But the real core of the intelligence, the truly smart part, has to be the self-auditing loop. This is the engine of refinement.
This is the core differentiator, and it's brilliant in its simplicity. The LLM, guided by the meta adapter's structured prompt, outputs the solution in the form of ASCII grid code. It's essentially a Python-like function that describes the required transformation, something like filter Redandrate 90.
Okay.
This code is executed immediately in a secured sandbox environment. The resulting grid produced by the code is then scored instantly against the demonstration cases provided in the ARC task.
So the model doesn't just guess the answer. It writes a program, runs the program, and then sees if its program successfully transformed all the input examples into the required output examples.
Exactly. And the criteria for success are strict. The system only continues to iterate and refine if the match score against the training demonstrations is less than 95%. This focused self-correction is what makes it hyper-efficient. On average, the system only requires 1.2 iterations. If the first program works, it stops. If it finds a minor bug, it refines the program and tries again.
This is where that shocking token efficiency comes in, right? That 96 tokens versus 138,000 example.
Yeah.
Let's make sure we put a spotlight on that token usage difference because it's almost unbelievable.
It is the defining metric of architectural intelligence versus brute force. For a notoriously complex task like 4CD 1B7B2, Poetiq system used only 96 tokens for the entire auditing phase.
96.
And why? Because the system is auditing clean executable code against clear output metrics. Now, contrast that sharply with DeepThink, which required a staggering 138,000 tokens for the same task.
138,000.
DeepThink relies on continuously reprompting the massive LLM with all these various contextual hints and recursive internal thoughts, just hoping that eventually the brute force of computation will stumble upon the answer. Poetiq system uses computation only to verify a structured hypothesis.
Wait, 96 tokens versus 138,000.
Yeah.
That's like the difference between asking a master architect to check their own blueprint for a single missing support column versus asking 1,000 novices to debate the structural integrity of the entire building repeatedly until they accidentally name the right column.
That's a great way to put it.
That efficiency gap is purely enabled by structured architectural design.
It's the difference between structured hypothesis testing and high compute brute force guesswork. And on top of that, they employed some really critical efficiency hacks. They used dynamic token budgeting, which utilizes features like the thinking level, low-high in the Gemini 3 API to optimize resource usage based on the perceived difficulty of the task. They also included specific low-level details like color-aware parsing, for example, interpreting the input text 5 gray instead of relying on ambiguous natural language. And crucially, they adhered strictly to ARC rules by using no external web searches or tools, ensuring the reasoning is truly endogenous to the system's own architecture.
Okay, now we have to address the comparison that everyone in the source material is making. Draw the connection for us. Why is this Poetiq scaffolding considered a foundational architectural leap, similar to the 2017 Transformer paper, Attention is All You Need?
It is a profound parallel, and it's rooted in architectural efficiency. Back in 2017, the Transformer model was this massive breakthrough because it replaced older sequential networks, recurrent neural networks, or RNNs, with the attention mechanism. This allowed for massive parallelization of training and inference.
Right.
This not only boosted generalization capabilities dramatically, but also cut training costs by an order of magnitude, 10x. That architectural change is what enabled the massive LLMs we have today.
And as we establish the raw scale of those models, with their huge parameter counts and million token context windows, have begun hitting a wall when it came to fluid reasoning. We even saw models with mixture of experts, or MOE architecture, which is already a complexity boost intended for efficiency and specialization, still only hitting low scores. For example, Gemini 2.5 Pro only hit 4.9% on ARC-AGI-2 before this breakthrough.
That's right. The MOE architecture aims for efficiency in training and retrieval by activating only certain experts within the model for a given task, but it still suffered from the same lack of statefulness and structured reasoning on novel abstract tasks. Poetic scaffolding is the attention leap for the reasoning phase. It's a lightweight meta layer that amplifies the base capabilities of any sufficiently powerful foundation model by 1.7 times without requiring a single parameter tweak or retraining the underlying LLM.
Wow.
Just as transformers introduce self-attention to process input context efficiently, Poetiq's audit loop enables self-reasoning, where the model iteratively attends to, processes, and corrects its own output, its own errors, in a structured, efficient way.
So instead of trying to make the LLM larger or more complex with technologies like MOE, they gave the existing powerful LLM a state machine, a mirror, and a debug tool.
Precisely. We saw a critical shift in scaling dynamics. Before 2025, reasoning scaled logarithmically 100 times. The compute yielded only about a 2x increase in ARC score. Post-Poetiq, gains are linear, driven by architectural intelligence. They achieved 54% accuracy at 38 times the baseline cost, yes, but they achieved 2x the efficiency compared to previous high compute attempts that only scraped 45%. The X discourse cited in the sources nailed the conclusion. Current models are powerful enough for AGI, they just need the right agent scaffold. This is the core message. It democratizes the pursuit of superintelligence by showing we don't need $3,000 per puzzle compute budgets, we just need $30 in the right architecture.
That concept of democratization is so vital. For the listener who might be a developer, a startup founder, or in an enterprise prototyping solutions, this system fundamentally lowers the barrier to entry. It moves high-level reasoning from the realm of multi-billion-dollar labs to anyone with an API key and a decent idea.
The speed of integration is perhaps the most impressive practical aspect. The sources highlight that implementation takes mere hours, not months of specialized fine-tuning or training data collection.
Hours.
The process is simple. Clone the GitHub repository, input your API keys for Gemini or GPT, and make a simple configuration tweak. For instance, setting budget $20 automatically engages the orchestration layer to optimize the sequence of calls and refinement steps to stay within that financial constraint while maximizing accuracy.
And reliability is crucial when you're talking about integrating systems like this. The sources confirm 90% reproducibility.
That reproducibility, when you couple it with the staggering cost reduction, is revolutionary for deployment. We need to internalize that cost difference again. $31 per task with Poetiq versus $2,200 for high compute alternatives like Claude Opus 4.5 that failed to achieve the same score.
It's not even in the same ballpark.
It eliminates the necessity of having massive, dedicated GPU clusters or immense capital just to attempt complex reasoning tasks. It allows small teams to compete on architectural intelligence rather than resource accumulation.
And for the open source community, those who don't want to pay $31, the accessibility of the core structural components is a huge boon.
Absolutely. The open source meta adapter itself, which only contains 0.1 billion parameters, can run easily on consumer GPUs and costs just 0.0011 per task. That democratizes the foundational reasoning infrastructure. We're already seeing real-world confirmation of this in developer forums. Posts on Repcelerate, for instance, confirm that independent developers are enhancing open source models like Llama 3.1 by plus 15% on ARC-AGI-1 for around 5 cents per task. The scaffolding is proving instantly useful and accessible.
This just accelerates innovation across the board, because if every independent developer can access this level of reasoning capability cheaply, it entirely shifts the competitive landscape.
And it has profound, immediate enterprise impact, especially concerning the costs of validation. Traditionally, refining LLM outputs, especially for critical tasks, required extensive RLHF or reinforcement learning from human feedback.
Okay, let's pause quickly and define RLHF for those listening.
Certainly. RLHF is the costly iterative process where human reviewers rank, score, and provide preference feedback on large volumes of model outputs. This feedback is then used to fine-tune a reward model, which in turn teaches the main LLM to generate more helpful, safer, and higher quality results. It's essential for deploying quality models, but it is extremely time-consuming and expensive, often costing tens of millions of dollars for a major foundational model update.
So how does the Poetiq system cut those costs?
Because the Poetiq system can automatically audit code and reasoning pathways against defined logic, that 95% match criteria against examples enterprises can cut their costly, slow RLHF processes by 50% or more. The system provides immediate programmatic feedback, reducing the reliance on human labelers for structural consistency checks. This directly impacts R&D budgets globally. As one source put it, the ability to build stateful multi-actor systems is now available to indie labs, not just the big labs that can afford vast RLHF pipelines.
Okay, so we've established that the Poetiq system is smart and cheap. But for this to truly be the architectural leap toward AGI we're discussing, the scaffolding must demonstrate transferability. It can't just be an ARC-AGI-2 cheat code.
Right.
If the system is truly general, its gains on colored grids must hold true for entirely different non-grid-based problems. What did the sources confirm regarding performance transfer?
The transfer results, while some initial reports are still awaiting full independent verification, show really strong directional promise. They confirm the generality of the underlying reasoning architecture. For instance, on GPQA Diamond, which is a notoriously difficult general knowledge and scientific reasoning benchmark, the Poetiq system boosted performance by 5%, pushing the score up to 91.9%.
That test is about highly nuanced scientific context and difficult deduction, totally different from grid transformation. How does the audit loop even apply there?
So in the GPQA context, the system doesn't execute code, but it executes knowledge verification. The audit loop requires the LLM to output a chain of reasoning, which the scaffolding then uses to check for internal consistency and external factual coherence using a limited knowledge base. If the steps conflict or rely on a shaky premise, the system refines the plan. The code is replaced by a reasoning sequence. And the generality is further proven in mathematical domains, which require entirely different forms of symbolic manipulation. On the Advanced International Math Contest, AING 2025, performance was boosted by 3%, reaching 95%.
95%.
This gain is achieved because the audit loop for AIM tasks treats mathematical calculation as the execution step. The system writes the mathematical derivation, executes the calculation in an external verified engine like a Python interpreter or a symbolic algebra engine, and then audits the calculated result against the expected format and logical steps. It's leveraging the same 5-step structural framework.
And for something like OS navigation, OS world, that seems even further afield, interacting with a simulated operating system.
Yes. Osworld involves complex tasks like debugging a system or changing settings by navigating a virtual desktop and using command line interfaces. The Poetiq system showed a strong generality signal here, boosting performance to 61.4%. In this case, the code is the sequence of commands and mouse clicks. The sandbox is the simulated OS environment, and the audit checks whether the final system state matches the required goal state. This transferred to Osworld and also to International Olympiad in Informatics IOI Gold Medal Math Challenges signals that the refinement loop works robustly across fundamentally different modalities and reasoning types.
And finally, we should probably note the sustainability angle here. When we talk about 38x greater compute efficiency, that has tangible environmental benefits.
It absolutely does. When you are 38 times more compute efficient than the high compute models previously deployed, you are substantially reducing the carbon footprint of achieving these high reasoning goals. The sources confirm that this efficiency essentially halves the overall carbon expenditure compared to the brute force high compute models. Poetiq proves that smart architecture is, in fact, green architecture, mitigating that public concern that AI progress must necessarily be compute-heavy and environmentally costly.
Poetiq has hit 54%, right near the human baseline of 60%, and they did it in a matter of weeks. The sources clearly indicate they are not stopping there. So what is the roadmap for achieving and surpassing human parity in fluid reasoning?
Well, Poetiq has incredibly aggressive targets for the first quarter of 2026. They are aiming for 60% and higher using what they call internal iteration, meaning continuous refinement and fine-tuning of the lightweight meta-adapter using vast amounts of synthetic ARC-like data. This process ensures they continuously improve their strategy generation without risking data leakage from the private evaluation sets.
What are the immediate steps? Let's look at their December 2025 target.
The immediate goal involves advanced ensemble methods. Since the scaffolding is model agnostic, they plan to combine their current primary system, which is centered on Gemini 3, with other highly capable foundational models, specifically Grok 4, which has a reported base score of 37.6% on ARC-AGI-2.
So they're combining the best of different models.
Exactly. Their internal projections suggest a plus 4% gain from this advanced multi-LLM orchestration approach. They are leveraging the fact that different foundational models fail on different types of problems. By orchestrating them through the audit loop, they combine their strengths to cover a wider array of reasoning challenges.
And then, the next step in January 2026 sounds like a major architectural refinement, putting the self-correction mechanism itself under the microscope using RLHF.
That is the big move. They plan to use reinforcement learning from human feedback directly on the audit steps, so teaching the system not just to correct, but how to correct better when its first attempts fail. This involves a surprisingly modest budget, about $10,000 in compute, using 1 million trajectories of human-verified successful refinement paths.
And what's the target for that?
This phase specifically targets the most stubborn, unsolved V2 tasks, like those involving massive 30 by 30 grids or known failures like task 891232D6. The goal is efficiency, even with the added complexity, keeping the system lean and aiming for less than 1.5 API calls per task on average.
So they're refining the metadapter to be an expert in failure recovery. If they achieve those milestones, where does that put them on the overall score?
The internal modeling is highly optimistic. A key milestone involves verifying transferability across difficulty levels. If they can confirm a plus 3% transfer from the refined model back to the harder V2 tasks, similar to the gains they saw when adapting the system to V1, they would immediately hit 57% accuracy.
57%.
Full human parity, which they define as 62%, is projected to be achievable at around $40 per task, factoring in the added RLHF complexity. External analysis by the ARC prize community suggests that iterated refinement, meaning architectural scaling like this, scales at 2x per year. Based on Poetiq's initial adaptation rate, extrapolation suggests they could reach 65% accuracy by Q1 2026.
That trajectory from 31% to 65% in roughly 4 months, purely through software architecture, is frankly mind-boggling. Now, while the Poetiq system was born out of visual reasoning with grids, the underlying methodology is fundamentally general. Explain how this grid-to-code paradigm extends seamlessly to natural language and text generation.
The transition is elegant and conceptually clean. In the ARC context, the system takes visual input, plans, and outputs ASCII grid code for execution. In a text generation context, you just replace the ASCII parsing with NLP pipelines. The system would take a prompt, say, write a novel chapter about X, plan a narrative structure, output the text, execute a check in a text sandbox, the audit, and then refine the narrative.
So the core loop plan, code, test, audit, refine is applied to words, concepts, and facts instead of colored squares and functions. What does the text sandbox do specifically for text generation?
The text sandbox takes the generated text and runs targeted analyses. It acts as a coherence analyzer and a fact checker. For creative writing, the audit checks for plot consistency, character memory adherence, and temporal logic, all the areas where current raw LLMs often fail in long-form generation.
Right.
For high-stakes factual generation, the audit involves semantic extraction and verification against index knowledge sources. The system literally runs a script to find inconsistencies, and if it finds them, it instructs the LLM to rewrite and refine the conflicted paragraph.
What are the specific future use cases cited in the source material for this text adaptation?
We see significant projections across multiple domains, especially those requiring high fidelity. In coding, they anticipate a major jump. SWE Bench, which evaluates software engineering capability by requiring the model to fix bugs in real repositories, is projected to jump from 77.2%, which Claude 4.5 achieved, to 85% via these iterative audit loops.
Wow.
On LiveCode Bench Pro, which is a real-time coding competition benchmark, the ELO score for their system is expected to increase from 2439 ELO to 2600.
That 2600 ELO score is typically reserved for genuinely elite top 1% human programmers.
Exactly. The audited loop turns a competent senior engineer into a truly elite self-debugging programmer. For creative writing, like novels or role-playing scripts where self-audits are focused on plot consistency and character voice, early internal tests, they call them RBARD tests, project a coherence increase of plus 20%, addressing that common failure mode of forgetting earlier plot points in long narratives.
And for high-stakes reasoning, like advanced fact-checking in complex documents.
This is perhaps the most crucial domain. On the extremely difficult Humanities Last Exam, or HLE, which tests deep multidisciplinary knowledge, the Poetiq loop is projected to deliver a plus 10% gain via iterative systematic fact checks. This turns a highly uncertain score into verifiable knowledge through systematic refinement. The ultimate future vision, Poetiq Text V1, which is slated for Q1 2026, aims for hybrid reasoning, seamlessly blending grid and text tasks, for example, automatically generating a detailed, audited report based on diagrammatic inputs or complex process flowcharts. So, to synthesize this whole deep dive, the core conclusion is pretty definitive. Poetiq proves that the pursuit of artificial general intelligence and highly capable reasoning systems isn't just about massive parameter count, huge context windows, or spending billions on GPUs. It is fundamentally about scaffolding on steroids, the lightweight, hyper-efficient architectural design of the reasoning process itself.
The breakthrough is not just hitting 54% on ARC-AGI-2. The breakthrough is democratizing AGI progress by proving that the already immensely powerful foundation models we have are sufficient, provided they are structured correctly with this multi-step self-auditing architecture. The innovation is in solving how to solve anything, not just solving one particular benchmark task. This shifts the focus of AI R&D from chip foundries to software design labs.
The focus has irrevocably shifted from raw scale to smart system design. And because the system works by executing code and systematically auditing its own mistakes, and doing so with rapidly decreasing costs, it suggests that highly scalable, self-correcting intelligence is no longer theoretical, but deployable today.
So here is the final provocative thought for you, the listener, to mull over as you think about the implications of this breakthrough. We've seen that the cost of iterative audited reasoning is dropping exponentially, from $2,200 down to $31 per task, and potentially much lower via open-source tools. The systems are now auditing their own mistakes using verifiable code execution consistency checks. So if efficiency continues to scale this rapidly, what is the first major real-world industry, and think beyond just code generation, where the cost of iterative audited reasoning drops low enough to truly replace human expert oversight entirely?